Let's now solve a few problems on the singularities of a holomorphic function. The first problem is on removable singularities. So let me note the problem down for you. Let f be a function which is holomorphic on a punctured neighborhood of a point R. So basically removing the point z0, let it be holomorphic there. Basically z0 is an isolated singularity, be a holomorphic function which satisfies the condition such that the imaginary part of f of z is greater than 0. Suppose for all z in the punctured disk dz0 or minus z0 we have the imaginary part of f of z is greater than 0, then prove that z0 is a removable singularity. Let's give a solution. The problem will be solved by an application of the Riemann removable singularity theorem in some sense. However, imaginary part of z greater than 0, which is the upper half plane, is not a bounded function necessarily, and therefore the Riemann removable singularity theorem cannot be used in the exact form that is available to us. So rather what we will use is that we know there is a map from the upper half space into the unit disk, which we have referred to once earlier. Consider the following map. Consider the function, the Mobius transformation phi of z, which is given by z minus I by z plus I. So if you notice, this Mobius transformation is holomorphic away from minus I. In particular, in the set of all z such that imaginary part of z is greater than 0, where minus I does not belong to, this function is holomorphic, and we know that it can be inverted there. The function is holomorphic with inverse given by phi inverse of z, which is I times 1 plus z by 1 minus z. So I know the inverse explicitly, so it's your job to sit down and check that phi inverse indeed is the inverse of phi that is written here. An exercise for you to sit down and check would be that phi maps the upper half space onto the unit disk. So the easier way to check this exercise would be that phi indeed maps H into the unit disk and that it maps D into the upper half space. Right, so once we have this, let's now get back to our problem. What is the problem telling us? The problem is telling us that the imaginary part of f of z. So what was H here, by the way? Where H, the upper half space, is the set of all z in C, where the imaginary part of z is greater than 0, and D is the unit disk. Now getting back to our problem, the imaginary part of f of z is greater than 0 for all z in D z0 or minus z0. Well, that means that f is a map from D z0 or minus z0 into H, right? And by composing it with phi, hence by composition with phi, we have phi composed with f is now a map from D z0 r minus z0 into the unit disk. Now, how is the situation to apply the Riemann removable singularity theorem? The reason being that disk is the set of all z such that mod z is less than 1. So in particular, phi composed with f has an isolated singularity and it is bounded in a neighborhood of z0. By Riemann removable singularity theorem, There exists a function g holomorphic on dz0r such that phi composed with f of z is equal to g of z on dz0r minus z0. Now, the key thing is that G is going to map dz0r into the set of all z such that mod z is less than or equal to 1, right? By the open mapping theorem, by applying the open mapping theorem, notice that open mapping theorem is necessary to ensure that G of z0 is not having unit modulus. By open mapping theorem, G of z0 is going to be in the unit disk. G is going to be a map from dz0r into the unit disk. That is good because now if you compose with phi inverse, by composing with phi inverse, which is a map from D to H, this composition makes sense. We have f of z is equal to P inverse composed with G of z on dz0r minus z0, and phi inverse composed with G is holomorphic on dz0r. And therefore, which tells us that z0 is a removable singularity by the very definition of removable singularity. Removable singularity of f. So the next problem is about the behavior of a holomorphic function around a pole. If you recall the definition of a pole, z0 is a pole when, as we approach z0, the limit of the absolute value blows up. The limit as z goes to z0 of absolute value of f of z is infinite. In this problem, what we will do is that we will show that the image of dz0 r minus z0 will contain the complement of a disk of some radius. It's a much stronger property than the definition, isn't it? So let me write down the problem so that it will be clearer. Let z0 be a pole of a function f which is defined on dz0 r minus z0 into c. Then prove that there exists some capital R greater than 0 such that the set of all z in C with mod z greater than R is contained in f of dz0r minus z0. Let's try to prove this problem. If you go back and check the behavior of a pole, so suppose our z0 is a pole of order m. Okay, let z0 be a pole of order m. We may assume without loss of generality that on dz0 r minus z0 f does not vanish. Let's assume that f of z is not equal to 0 on dz0 r minus z0. This can be certainly assumed because after all, if you shrink it a bit, the fact that the absolute value of f of z blows up exactly means that for some smaller disk it's greater than some capital M. So this can certainly be assumed, and because it's a pole of order m, then there exists some function g which is now having a removable singularity, which hence will be defined on dz0r into c with g of z not equal to 0 on dz0r such that on dz0r minus z0 we have our function f of z is equal to g of z by z minus z0 to the power m. This is precisely the definition of a pole of order m. So G is not going to vanish over there. And let us now define the function h to be, let h be the function 1 by f of z. That's going to be equal to z minus z0 to the power m times g of z. So let me just call h to be equal to h1 to be equal to 1 by f of z on dz0 r minus z0. And immediately we know from our theory that we have developed that h1 has a removable singularity at z0, and further, and that h1 of z0 is equal to 0. So this is something which we will certainly maybe I shouldn't write h of z0 is equal to 0, where h extends, let me just put it this way, h extends h0. If h0 has a removable singularity at z0, that means that in dz0 r there is a holomorphic function h such that h of z is equal to h1 of z on dz0 r minus z0. So I have just captured all that by saying that h extends h0, maybe I should just add dz to dz0 r. So now we have a function h here which is defined and holomorphic on dz0r and which maps z0 to 0. Now again, let me use the open mapping theorem. Let's just see how powerful the open mapping theorem is. By the open mapping theorem, and the fact that h is not identically a constant function, since h is not a constant, h of z0 is going to be an interior point. That means their x is epsilon positive such that d 0 epsilon is contained in f of dz0 r, right? That means that not f, h. It means that any point in the disk of radius epsilon around 0 is in the image of dz0r under h because of the open mapping theorem. Remember that h is defined on dz0r. In fact, we can say a little more. If w now be in C such that mod w, or rather mod w is greater than 1 by epsilon. Let me call this 1 by epsilon to be capital R. Suppose this is the case, this would imply that 1 by w belongs to d0 epsilon, right? 1 by w will now have, in particular, w is not 0, remember that. So 1 by w is going to be in d0 epsilon, and since w is not equal to 0, remember that h maps only z0 to 0, and therefore w, there exists some z in dz0 r minus z0 such that 1 by w is equal to h of z. But now let's go back to the definition. What was our h? H was basically away from dz0 r, away from z0, this is nothing but h1 of z. And what was h1 of z? h1 of z is just 1 by f of z, right? So this is going to be equal to 1 by f of z. This implies that f of z is equal to w. So that means you take any arbitrary point w in C which satisfies the condition that mod w is greater than r, hence the set of all w such that mod w is greater than r is contained in f of dz0 r minus the isolated singularity. And that's precisely what we had set out to prove. If I go up and show you the problem, that's precisely what we were asked to prove. Let's now consider another problem where our singularity has certain specific behavior. So let f from dz0 R minus Z0 into C be a holomorphic function. That means that it has an isolated singularity at Z0 such that the real part of f of z is less than some r for some real number r. And for all z in dz0 r minus z0. So the real part is bounded above on the punctured disk of radius r. If this happens, even then f has a removable singularity at z0. Let's try to give a proof of this. So basically the condition that we are given is that the real part of f of z is bounded on dz0 r minus z0. So what are the type of singularities that can happen? F can either have a removable singularity, or it can have a pole, or it can have an essential singularity. One of these three should necessarily happen. We will show that f cannot have a pole or that it cannot have an essential singularity. We will come to a contradiction in either cases. Suppose Z0 is a pole. Of f. Then what will happen? Then by our previous problem, we know that there is some capital R. So maybe the R's shouldn't be confused. There is some R fixed here. Maybe I should change it to M. Yeah, maybe let me change it to N so that I can work freely with R's. So by the previous problem, if Z0 is a pole, there exists some capital R greater than 0 such that the set of all z with mod z greater than R is contained in f of dz0 R minus z0. This is something which we have ensured. Now let's pick some point, let W be a point in C which has the properties mod W greater than R and such that the real part of W is greater than M. This can certainly be arranged. You can get hold of one W which satisfies the condition which we don't want here. Right? Now what will happen here? By the condition star, we will be able to get hold of some pre-image of W in dz0 r minus z0. There exists z in dz0 r minus z0 by star such that f of z is equal to W. That would imply that the real part of f of z is equal to the real part of W, which is greater than M for z in dz0 r minus z0, which is a contradiction. Because if you go up and check the hypothesis in the problem, we have put the restriction that for every z in dz0 r minus z0, our real part of f of z is less than M. And we just ensured that this is going to happen. This is going to be violated. And therefore, we have ruled out the possibility that z0 is a pole. And z0 cannot be a pole. So the contradiction came up because we assumed that z0 is a pole. Let's now rule out the possibility that z0 is an essential singularity. Suppose z0 is an essential singularity. Let's come to some kind of a contradiction. Here we are going to use the Casserati-Weierstrass theorem. What did Casserati-Weierstrass theorem tell us? By the Casserati-Weierstrass theorem, f of dz0r minus z0 is dense in C. That's what it said, right? For every alpha in C, there exists some sequence Zn let me recall the statement for you. Given W in C, there exists a sequence Zn converging to Z0, a sequence converging to the singularity such that f of Zn converges to W. In fact, this is a stronger statement than demanding that dz0r minus z0 is dense. In fact, the exact statement would be equivalent to this would be for any epsilon positive where epsilon is less than r, then f of d z0 epsilon minus z0 is dense in C. That will be the equivalent of whatever is written inside the bracket here. But anyway, we have in dz0 r minus z0 a sequence which converges to W, where W is again going to be picked as above. Let W be a point in the complex plane such that the real part of W is greater than M. Again, a condition which is going to give us the contradiction. And let Zn be a sequence by the Casserati-Weierstrass theorem in dz0 r minus z0 such that Zn converges to Z0 and f of Zn converges to W. This is ensured by the Casserati-Weierstrass theorem. This tells us that there exists some capital N by the very definition of convergence. When f of Zn converges to W, the real part of f of Zn converges to the real part of W, and therefore there is some N such that for all N greater than capital N, we have the real part of f of Zn is greater than M, because the real part of W is greater than M. So the convergence ensures that this happens, which is again a contradiction, because now we have found a sequence, in fact, of points, in fact a sequence of points Zn such that the real part of f of Zn is going to be greater than M, and therefore Z0 cannot be an essential singularity. So of the three possible isolated singularities that are possible, we have ruled out pole and an essential singularity, and therefore this is forced to be a removable singularity. So the next problem is going to deal with how the behavior of an isolated singularity changes when we exponentiate a given function which has an isolated singularity. Let me write down the problem and then we will see a proof of it, a solution to it rather. Let Z0 be an isolated singularity of a function f. That means that f is holomorphic on dz0r minus z0. I'm not talking about the type of isolated singularity. The problem here is to show that then the function e to the power f, which is the composition of the exponentiation with the function f, does not have a pole at z0. Notice that z0 is still an isolated singularity of e to the power f, because this is a function which is still defined on dz0r minus z0. However, we can now for sure say that it cannot have a pole at z0. It will either be a removable singularity or it will be an essential singularity. That is the essence of the problem. In fact, we will prove exactly what happens when z0 is a removable singularity and what will happen when z0 is a pole and when z0 is an essential singularity of small f. Let's consider all these cases separately. Suppose we have z0 as a removable singularity. Let z0 be a removable singularity. This is the simplest case, i.e. there exists g in dz0r holomorphic such that f of z is equal to g of z on dz0r minus z0, where dz0r minus z0 is where our function f is defined. We don't know its behavior at z0. suppose it's a removable singularity, we can get hold of one such function g. That would imply that e to the power f of z is equal to e to the power g of z for all z in this particular set. But then e to the power g of z is a holomorphic function on dz0r, because exponential is a entire function and g is a function which is defined on dz0r, which means that e to the power f has a removable singularity. At z0. So if z0 is a removable singularity of f, then z0 is necessarily a removable singularity of e to the power f as well. Now let's consider the case when z0 is a pole. Let z0 be a pole of f. Let's now show that z0 cannot be a removable singularity or a pole of e to the power f. In fact, we will come to a contradiction if z0 is either a removable singularity or a pole of e to the power f. Let's assume, suppose z0 is a removable singularity of e to the power f. Remember that e to the power f is just composition of exponential function with the function small f. And suppose z0 is a removable singularity. What does that mean? That means that the absolute value of e to the power f of z, this is less than some number m for by going down to a smaller neighborhood if needed. By continuity, we do have this. I'll just call the same r as the radius of the disk concerned. So we will have that e to the power f of z has absolute value less than m here. But what is the absolute value of e to the power w for some w which is equal to a to the power a plus ib? That's going to be equal to e to the power a, which is basically e to the power real part of w, right? So this means that e to the power real part of f of z, this is going to be less than m. Now these are some real numbers, and by taking the logarithm we get to conclude that real part of f of z, so remember that m is some positive number here, so this is going to be less than some m prime for all z in dz0r minus z0. But by the previous problem, what did we conclude if the real part of f of z is less than m prime? This helps us conclude that f has a removable singularity at z0, isn't it? But if you go up and check, we assumed that z0 is a pole of f. So if z0 is a removable singularity of e to the power f, we ended up concluding that z0 is also a removable singularity of f, which is a contradiction. So in particular, if z0 is a pole of if z0 is a pole of f, then z0 cannot be a removable singularity of e to the power f. Now what if z0 is a pole of e to the power f? That would mean that e to the power minus f has a removable singularity at z0, isn't it? That's by the very definition. In fact, at z0, e to the power minus f is going to be 0. If z0 is a pole of e to the power f, 1 by e to the power f will have a 0 at z0 after removing the singularity. It's going to be a removable singularity. But then, if z0 is a removable singularity of e to the power f, we concluded that f has a removable singularity at z0, right? And using this argument, by the argument above, we have z0 is a removable singularity of minus f, but then that would imply that z0 is a removable singularity of f as well. If Z0 is a removable singularity of minus f, then Z0 is going to be a removable singularity of f as well. But that's going to be a contradiction to the assumption that Z0 is a pole, right? We started off again with the assumption that Z0 is a. So hence, if Z0 happens to be a pole of f, then both the cases of Z0 being a removable singularity of e to the power f or Z0 being a pole of e to the power f are ruled out. And thus, Z0 is an essential singularity. There are only three possibilities for an isolated singularity, and that's precisely what we have. So what let's just go back and see what we have done. We have checked the following. We have checked that if Z0 is a removable singularity, then e to the power f has a removable singularity at Z0. Then the next conclusion was, if Z0 is a pole of f, then we have Z0 is an essential singularity of Z0. Z0 is an essential singularity of e to the power f. I'm sorry. And so finally, we are only left with one case. What happens when Z0 is an essential singularity of f? So let Z0 now be an essential singularity. And in this case, we are going to use the Casserati Weierstrass theorem to establish that Z0 is going to be an essential singularity of e to the power f as well. The key thing to note is that exponential is a map from the complex plane to c minus 0, and it's a continuous function. So hence, by Casserati Weierstrass theorem, again let me just write the statement down as f of d z0 r minus z0. If you look at this function's closure, that is going to be equal to c. Now, being a continuous function, since e or exp is continuous, exp of f of d z0 r minus z0 bar, this is going to be contained in exp of f of d of z0 r minus z0 closure. And therefore, this is basically c. So this is going to tell us that c star, c minus 0, is contained in this closed set, which means that the exp of f of d z0 r minus z0 closure is going to be equal to c. And that tells us that maybe this step which I am writing down as a last step is a minute's thought. This is going to be an essential singularity. This cannot happen. This particular condition cannot happen if Z0 is a removable singularity or a pole. Therefore, Z is going to be an essential singularity. So we now know exactly how the behavior of an isolated singularity changes when we exponentiate our given function. In the next problem, we will discuss the behavior of a function which is holomorphic on a given set omega minus a set S, which not necessarily is discrete. We have not really studied singularities which are not isolated. This is however going to use techniques from Casserati Weierstrass theorem very crucially and say something about singularities which are not isolated. This is more of a fun exercise. So let f be a function from omega minus z0, z1, z2 and so on, where omega is open connected and Zn is a sequence which converges to Z0 in omega. So basically Zn and Z0 are all points in omega, Zn converges to Z0. So this is a converging sequence along with its limit point. So notice that the thing inside this bracket, this is not a discrete set, Z0 is a limit point. So we have a function which is holomorphic. Oh, I didn't write that. Let f be a holomorphic function on such a set. Assume further that Zn for n greater than 0 basically z1, z2, z3, all these points are poles of f. Let z1, z2, so on be poles of f. Then the statement of Casserati-Weierstrass theorem is true for such a function as well. Then given epsilon positive, the image of dz0 epsilon minus the singularities z1, z2 and so on. F of this is dense in C. So we are going to mimic the proof of Casserati-Weierstrass theorem here. So consider a complex number alpha in C such that alpha is not in the closure. So let me, do I have to write it? Yeah, let me just write it fully. Alpha is not in the closure of dz0 epsilon minus z0 z1 and so on. This is a closed set and alpha is in the complement. That implies that there exists some delta positive such that d alpha delta intersected with f of dz0 epsilon minus z0 z1 closure is empty. So let's do the exact same thing that we did earlier. Define g of z to be equal to 1 by f of z minus alpha. So notice that f of z is not going to be equal to alpha ever. In fact, f of z doesn't take values in a neighborhood of alpha, and therefore 1 by f of z minus alpha makes sense. This is defined on omega minus z0, z1 and so on. Now if you focus on mod g of z, this is going to be 1 by f of z minus alpha's absolute value, which is in fact less than 1 by delta. So this is bounded on this omega minus z0, z1, z2 and so on. Also, if you consider zn for n greater than 0 is an isolated singularity of f. They are a sequence which is converging to z0. They are all isolated singularities of f. So let me add one criterion here. Is a sequence of distinct points. Otherwise, this statement which I just mentioned will not be right. This is condition is imposed. So the sequence is going to be distinct, and therefore each of these points is going to be an isolated singularity of f. And what did we just check out? We checked out that G is bounded in a neighborhood of each of these isolated singularities, which tells us that G has a removable singularity at Zn for all n greater than 0. Z0 we will come to at the very end. But what do we know about our function f? We know that Zn for every n greater than 0 is a pole of our function, right? Since Zn is a pole of f, what do we have? We have g of Zn is equal to 0. Remember that g of z is 1 by f of z minus alpha. So as we approach the points Zn, the absolute value goes up, and therefore 1 by f of Zn minus alpha also will f of 1 by f of z minus alpha will also converge to 0 as z approaches Zn for each n, and therefore we have g of Zn is going to be equal to 0. So this tells us that G is now defined on dz0 r minus z0 and hence Z0 is a removable singularity. And moreover, if you just go up and check, we have this condition here, and on each of the points z and g of zn is equal to 0, again g is locally bounded, which tells in the z0 minus r, which tells us that g has a removable singularity, and has a removable singularity because it is bounded in a neighborhood of z0, which tells us that you can extend past z0 as well, but we know that each of the zns are 0, and g of, as zn converges to z0, g of zn, because of continuity, by continuity g of z0 is equal to 0 by continuity. But now we are facing a contradiction, namely that we have a function g which is not identically equal to 0 and such that its 0 set has a limit point. Now notice that g is a non-zero function such that g of zn is equal to 0 for all n greater than or equal to 0, and such that the set z0, z1, so on has a limit point. That's a contradiction to the identity theorem, or the statement that the zeros of a holomorphic, non-zero holomorphic function are discrete, are isolated. This is a contradiction. Let me just write that it's a contradiction to the identity theorem. So notice how strongly all these theorems are being used. So all this happened because we considered some alpha which satisfied this condition, which we hence conclude that cannot happen. Hence, there does not exist such an alpha. That means that the image is going to be dense. Okay, let me conclude this problem session by trying to compute the Laurent series expansion of a particular function on different annuli. So the problem is the following. Consider the following rational function. Consider f of z given by 1 by z times z minus 1. This is a function which is holomorphic away from the origin and the point 1. So it has isolated singularities at 0 and 1. Prove that, or find the Laurent series expansion of f around, okay, in the following annuli. Let's work it out separately. Annuli is the plural for annulus. The first one is on D01 minus 0. Notice that on D01 minus 0, this function is holomorphic. How about on D11 minus 1? So this is the disk of radius 1 around 1 with the point 1 removed. And finally, the annulus, which is the set of all z's, is that mod z is greater than 1. Notice that in the case C as well, this particular function is holomorphic. Notice that these are all annuli, and in each of these annuli, our function is holomorphic. And therefore, we can talk about a Laurent series expansion in each of these annuli. Let's start with the first one. On D01, what do we know about 1 by z minus 1? We know that this is basically 1 by 1 minus z, and for mod z less than 1, we know that this has the series expansion summation z to the power n, where n is going to go from 0 to infinity. this power series expansion exists. Then for z not equal to 0, 1 by z times the power series, this is going to be equal to, by taking it in, because this series is convergent, we can always do that, not we can always, we can do this in this case. This is going to be z to the power n minus 1, where n is going from 0 to infinity, and this is precisely our z times z minus 1, and we have our power series expansion here. So this is exactly equal to 1 by z plus summation z to the power n, n going from 0 to infinity. So that's going to be the Laurent series expansion of 1 by z times z minus 1 on the, this is true for every z on d0 1 minus 0, and that is the reason why, by the uniqueness of coefficients, we get to conclude that this is the Laurent series expansion. How about when we focus our attention on d11? The techniques are not going to be very different. Then on d11, what is going to be 1 by z? We'll just rewrite this as 1 by 1 minus 1 minus z. Now on d11, 1 minus z will have absolute value less than 1. Again, we can talk about the power series expansion here. This is going to be 1 minus z to the power n, where n is going to go from 0 to infinity. So that's going to be 1 by z on d11. And because this series converges absolutely, for z not equal to 1, what is going to be 1 by z minus 1 times z. That's going to be equal to 1 by z minus 1 times this series, which is going to be equal to minus of summation n is equal to 0 to infinity 1 minus z to the power n minus 1. Yet again, we can write the expansion similarly as above. So that this is going to be the Laurent series expansion around 1 in a punctured disk of radius 1. Now that's the case with annuli which are having different centers. So this is an annulus which is centered at 0, this is an annulus which is centered at 1. But this annulus and this annulus both are centered at 0, if you notice. This is actually nothing but A0 1 infinity, right? This is the annulus which has R1 equal to 1 and R2 infinite. So what happens in C? Let's now get to what happens in C. Let's again do some manipulations and see what happens. Notice that Z is satisfying the condition that mod Z is greater than 1, right? On the set of all Z such that mod Z is greater than 1, what do we have? We have 1 by z minus 1 times z. This is just going to be equal to 1 by z square times 1 minus 1 by z. This is exactly what our series is going to behave like. Now mod z greater than 1 implies that 1 by z has absolute value less than 1. Therefore, I can write 1 by 1 minus z in the following power series. This is going to be 1 by z to the power n, where n goes from 0 to infinity, and that's going to be equal to n equal to now 0 to infinity of 1 by z to the power n plus 2, or this is equal to summation n is equal to 2 to infinity z to the power minus n. So notice that on two different annuli centered at 0, we have distinct Laurent series expansion. They are not similar. However, once we fix an annuli, we get to have a very unique power series expansion.